So the first question, this differential equation, what is the order and degree? So this is the second order, and the second order has degree 2. And throughout all other derivatives do not have a rational. It has a positive integer. So this is in the form of polynomial and derivatives. So order 2, degree 2. This is the correct answer. And most students have done it right. Okay. It is order 2 and degree 2. Next question. Now, order of the differential equation given like this: d cube y by dx cube plus 4 times under root of dy by dx whole cube plus y square equal to 0. Now, this is a differential equation. First thing what we need to do is to eliminate the radical sign of the differential equation. So it must be free from radical signs. So that means this is to the power half. So we can square it. When we square, we get 16 times dy by dx, the whole cube, plus y square. Now this is in the form of polynomial and derivatives. The highest order is 3, and the power of the highest order derivative is 2. So this is 3 and 2. The order is 3 and the degree is 2. So let's see how people have answered. Now this is the second question. So many mistakes. So the mistake made by the people is, so everyone has identified third order correct, but this is the mistake, degree 1, because one has just taken that the power of third derivative of y is 1 here, but we have to consider the power after removing all the radical signs. So that's what it is. Now let's look at the next question. Again, many students have not attempted the next question. So given the solution, we have to find the differential equation. In this case, which one of the following differential equation has this solution? So there's a solution. We have to find the differential equation. To find the differential equation, what we need to do is to differentiate it. Dy by dx gives us 5 cos 3x plus pi by 3 times 3. Again, let us differentiate. Second derivative, we'll get 5 into minus sine 3x plus pi by 3 times 3 in already 3 is there. Again, another 3 will come. So we get 9. Now, this is 5 sine 3x plus pi by 3 is y. So this term is y. So we get minus 9y. So the differential equation will be plus 9y equal to 0. Now you may ask me a legitimate question that why can't we differentiate it only once? Why did we differentiate twice? So the thing is, when you expand this is sine of ax plus b form. Even directly, you can see that there are two constants here. 5 is one constant and this is another constant. So there are two constants. So whenever the solution has two constants, that means the order of the differential equation is 2. In other words, we could write this as, um, y is equal to a sine 3x plus b cos 3x. Okay, this is when you expand. So again, there are two constants here, a and b. So two constants means we have to differentiate the solution twice to eliminate the constants. Then we get the differential equation. So this is the differential equation. So this is correct. Let us see. So many students made a mistake in this. Third one. So you have differentiated it only once. That's a mistake. But after differentiating, you see the derivative is not the same in the problem that we see. This 5 times 3 cos x plus pi by 3. Now, when you expand this, you will get a cos 3x term and a sin 3x term. However, here it is only cos 3x term. So these two are wrong. So this is correct. In fact, if you remember the simple harmonic motion equation, this is the differential equation of simple harmonic motion, and this is the solution to the displacement of the simple harmonic motion. Okay. So this is an important problem, very fundamental in nature. Okay, next, let's look at the next one. And this is straightforward. I'll not solve this on board. This directly for this equation to be exact. So term of dx, that is m, this should be partially differentiated with y. And the term associated with dy should be partially differentiated with respect to x. And both should be equal. So we get this as the answer. Dou m by dou y is equal to dou n by dou x. This is the correct answer. And I think most students have done this one right. Yes, everybody did this right. Okay. Now let's look at the next question. All right, this is a particular solution. Let's see. Most students did right. Some students, one of you have not attempted. So look here. So this is a differential equation. With a, although it has given a general solution, but actually it's a particular solution. Let us see this. This differential equation, which we can solve very, very simply by separation of variables. Just a second. Oh, something is wrong with the pen. These are, I think, okay. I think I annotated myself. All right, I'm unable to remove this anyway. Okay, let's look at this. Dy by dx is equal to minus 5y. Separate the variables. Now integrate. So we get log y is equal to minus 5x plus log c, we do. So y will be e power minus 5x plus log c, which is e power minus 5x. Okay, e power log c, which is c e power minus 5x. So y is equal to c into e power minus 5x. When x equal to 0, y is equal to 1. So this gives e power 0 is 1. So c is equal to 1. So the correct answer, c equal to 1. So solution is y is equal to e power minus 5x. Here is given in terms of t. So this is the correct answer. Next, this is a direct question. The differential equation dy by dx plus py equal to q is a linear equation if p and q are functions of x alone or constants. So this is the correct answer. Okay, so you can understand questions simple on the concepts also come in GATE. Then again, this is a simple question. Most of you have done it right. So here, by separation of variables, we can write this like this. Dy upon 1 plus y square is equal to dx, and upon integrating, we'll get tan inverse y is equal to x plus c. So y is tan of x plus c. So this is the correct option. Very, very simple. Orally we can do. Okay, many of you have not attempted this. Some of you have attempted this and got it right. So this is application of differential equations to problems. And this we have been doing even in, +2 in chemical kinetics kind of problems and nuclear fission kinds of problems, uh, radioactive decay kind of problems. So yeah, so yeah, see yeah. So biotransformation of an organic compound has concentration X, which can be modeled using an ordinary differential equation. So rate of change of concentration is proportional to the square of the concentration present. This is how the differential equation is defined. So this we can easily do separation of variables. We have to solve for this. Now when we integrate, we get x to the power -2 plus 1 by -2 plus 1 is equal to minus kt plus c. So we get -1 upon x minus 1 upon x is equal to minus kt plus c. So we get 1 by x is equal to kt minus c. Now the given condition is when x is equal to a, x is equal to a at t equal to 0. So use that condition. At t equal to 0, x is a. So we get 0 minus c. So minus c is 1 by a, c is equal to -1 by a. Therefore, the solution, and this is the solution. So substitute c. 1 by x is equal to kt plus 1 by. That's all. Very simple. It is. So this is the correct answer. 1 by x is equal to kt plus 1 by a. Very, very simple solution. Okay, this is Bernoulli's transformation, what we discussed yesterday. So there's a Bernoulli's equation, and we need to find the transformation. So dy by dt plus p of t times y is equal to q of t times y power n. So naturally we divide by 1 by y power n. Sorry, divide by y power n. So we get this pt y power 1 minus n is equal to q of t. Now we have to transform. So we put this as v. Okay. So given this is the substitution. Now derivative 1 minus n times y to the power minus n dy by dt is equal to dv by dt. So you get this 1 by y power n dy by dt is equal to 1 by 1 by 1 minus n dv by dt. Substitute that in this equation here. Here we need to substitute this with this. So 1 by 1 minus n dv by dt plus pt times v is equal to q of t. So the transformed equation dv by dt plus p times t into 1 minus n times v into 1 minus n times q. So what we observe in this equation, see, this is 1 plus n, 1 plus n, 1 plus n, 1 minus n, 1 minus n, 1 plus n. All these are wrong. Both 1 minus n. Of course, seeing this, you could directly say it, but just putting the steps. So this is the transformation. All right, next. Next, we deal with linear differential equation. Okay, now this is a linear differential equation. You can observe this. Divide by x square, we get dy by dx is 2 upon x times y is equal to 2 log x upon x cube. This is by dividing throughout by x square. This is what we get. So this is of the form dy by dx plus p of x times y is equal to q of x. So this is what we get. So integrating factor is e power integral p dx, which is e power integral 2 upon x dx, which is e power 2 log x, which becomes x square. The integrating factor is x square. So solution is integrating factor x square times the dependent variable into integrating factor times q dx. So we get x square y is equal to 2 log x upon x dx. So now let us integrate by parts. So 2 can be taken out. First function is logarithmic, second function is algebraic, second function is 1 upon x. So first function into integral of the second. So we get log x minus integral of derivative of the first and the integral of the second. Oh. So this is a repeating integral. So let us evaluate this separately. Integral log x by x dx. Let's say this is I. So first function into integral of the second minus integral of derivative of the first becomes 1 by x, integral of the second becomes log x. So again, it repeats. So this is log x whole square minus I. So I to I will be log x the whole square. So which means the integral is half log x square. Okay. So of course, integration by parts or by substitution also we can do this. By substituting log x as t, 1 by x dx will be dt. So 2t you will get 2t dt, t square is the answer. So this is equal to log x the whole square plus c. Now, when x is equal to 1, y is 0. So when x equal to 1, y is 0. So we get 0 on the left hand side, log 1 on the right hand side plus c, which implies c equal to 0. Therefore, x square y is equal to log x the whole square. This is the expression. So y is equal to log x the whole square by x square. Now the question is, what happens when y is equal to e? So y of e becomes log e, which is 1 upon e square. So you get 1 upon e square or e to the power minus 2. So this is the correct answer. So this was linear differential equation, the ones that we practiced a lot yesterday. And I have many questions from previous gate just on the first order differential equations. Just over a span of 10 years, 27 questions. Of course, from different departments, but this is one of the most important topics. You know, vector calculus, the way you can expect questions and differential equations, 100% you will get questions and get. Now this is again another linear differential equation. So divide by x square, you get dy by dx plus again 2 upon x, y is equal to, take this to the other side, x minus 1 by x square. So integrating factor is again e power 2 by x dx, which is e power 2 log x, which is x square. Solution is integrating factor times y is equal to integral of integrating factor times q dx. So x square cancels. So we get x square upon 2 minus x plus c, because we only get the numerator x minus 1. Integral will be x square by 2 minus x plus c. So y is 1 by 2 minus 1 by x plus c by x square. Now, when x equal to 1, y is equal to 0. So 0 is equal to half minus 1 plus c. So c is 1 minus half is equal to half. Therefore, the solution is y is equal to half minus 1 by x, and just substitute c here, plus 1 by 2x square. So compare, this is the correct answer. It was simple, just a solution to the linear differential equation. Oh, 10th one I missed. 11th one is this one. 10th question I missed. So 10th one. No, 10th we have done. I have not.
Sir, you did 10th, you just didn't.
I didn't put the answer. Okay. The last one, again, it's a linear differential equation. So this direct dy by dx, no transformation also required, very simple. Integrating factor will be e power integral 2x dx, which is e power x square. So solution is y times the integrating factor is equal to integral of the integrating factor times q dx plus c. So this is y e power minus, plus x square. This is integral 1 dx plus c. So it is x plus c. Now given when x is equal to 0, y is equal to 1. That's what is given. Y of 0 is 1. So substitute when x equal to 0, e power 0 is equal to 0 plus c, which means c is equal to 1. Therefore, we get y into e power x square is equal to x plus 1. So y is x plus 1 or 1 plus x into e power minus x square. So second one is the correct option. Okay. So where students are not answering is questions on linear differential equation and on this bio verbal problem. So other than that, most of it students have done. All right, so that was this part for today. Now let us move forward. Now we'll do so ordinary differential equations, first order and higher degree. So far we did first order and first degree, and there's so many questions from just first order and first degree. And they are very important ones. Now, the first order and higher degree. So let the differential equation be of the form uh, function of x, y, and dy by dx. All right. So let dy by dx be equal to p. Then the differential equation is x, y, function of x, y, and p. So now, first higher degree, first order and higher degree, they are different cases. Equations solvable for p. Meaning, this is a polynomial function in p, and we can solve for p, then that becomes easy. If the ODE, ordinary differential equation, is of the form a polynomial in p, p of n, and okay, now this is some function of x. This is dy by dx whole power n, and dy by dx whole power n minus 1 multiplied by some function of x. Suppose it's a differential equation like this. Now these p's can be uh, functions of x or functions of y also. Well, p can be function of y also. Okay. Now, if OD is of this form, and if the ODE can be resolved into linear factors as, say this, p minus f1 of x, p minus f2 of x. That means it's a polynomial, but I could resolve it into factors like this, nth degree polynomial, and I have n functions. So now each factor should be made equal to 0. Just a second. All right. Now, each factor, when equated to 0, gives a first order, first degree differential equation. First order, first degree differential equation. Okay. Now, so let's say the solution. Um, so the solution of the given higher order differential equation, no, a higher degree differential equation is then like this. The solution of the first factor equating to 0, then the solution multiplied by the solution of the second factor, multiplied by the solution of the third factor, multiplied by the solution of the nth factor. So there are n differential equations here: first, second, third, fourth, and so on up to n. So you have solutions for each of these. Note, you have the same constant. Reason? Because it is first order differential equation. So the order is 1. So the number of constants associated with the solution will be 1 only. Okay. So let us solve with an example. So solve dy by dx minus dx by dy is equal to x by y minus y upon x. So solution. So let dy by dx be is equal to p. So this becomes p minus 1 by p is equal to x by y minus y by x. So we get p square minus 1 is equal to x by y minus y by x times p. Okay. So this is p square minus of x by y minus y by x times p minus 1 equal to 0. So now can this be written in a form? So we can simplify this. We can write p times p minus x by y plus yeah, p times y by x minus this one we can written as x by y into y by x, this one. So we can get this as p times p minus x by y plus y by x you take out, you'll get p minus x by y. So we get two factors, p minus x by y times p plus y by x. Okay, is equal to 0. So we could solve this for p, solvable for dy by dx. Therefore, p minus xy equal to 0 and p plus y by x equal to 0. Now we get one solution here, one solution here. So from here we get dy by dx is equal to x upon y. So y dy is equal to x dx. Solving, that means integrating, we get y square by 2 is equal to x square by 2 plus c, or some c dash. And then we can write this as x square minus y square is equal to minus 2c dash, which is c. So x square minus y square is equal to c is one solution for solution for one. Now solution for this equation, dy by dx is equal to y upon x. So we get dy by y is equal to dx by x by separation of variables. Now integrating, we'll get log y is equal to log x plus, we can write log c. So y is equal to c times x. This is what we'll get, removing the log. Now the solution, sorry, a big mistake. This is minus, this is minus, this is minus. So I get c by x, not c. Therefore, the solution to the differential equation is x square minus y square minus c multiplied by xy minus c is equal to 0. This is xy minus c. So your solution should be such that when you should get c square, because it's a second degree equation. So the constant should have a square as its degree. So x square minus y square minus c and xy minus c. So this is an example of solving a problem which is solvable for p. Now, next, there are examples of different types where solvable for x or solvable for y. So, say case 2. So, there's a higher order differential equation. It's solvable for y or x. So let us take solvable for y and solvable for x is the same. So if the given equation is in the form y is equal to a function of x and dy by dx, then okay, then you see the what we do. I do dy by dx. dy by dx of this function. Now dy by dx is p, I know that. And I will get a function of another function of which may contain terms of x. It may contain term of the derivative, depends on what, and it will definitely contain the derivative of the derivative, the second derivative. But we are finding p. So what we have done is, now we have eliminated y completely from the picture. Okay. This new form is free from y. So that is solvable for y. Okay. Then the new differential equation is of the form f of x p and dp by dx. Instead of x, y and dy by dx, it is of this form, which may be solvable. Okay. The solution we can get, which okay, we'll look at one example. Solve. Y minus 2px is equal to p square mhm. No, it is tan inverse of p square. Tan inverse of x p square. So y could be written like this. Y is equal to 2px plus tan inverse of x p square. So now differentiating with respect to x, differentiating with respect to x, we get dy by dx on the left hand side, which is equal to p left hand side. Now is this p is differentiable and this is differentiable. So you get 2p into derivative of x plus 2x into derivative of p plus derivative of tan inverse is 1 by 1 plus x square times this derivative, that is p square plus 2xp times dp by dx. Remember, p is not just a constant, it's a function of x, dy by dx actually. Okay, so we get something like this. So we can try to simplify now. So let us collect dp by dx terms. So we get p plus p square upon 1 plus x square p power 4 term separate, plus I bring this p this side, then dp by dx times 2x plus 2xp 2xp by 1 plus x square p power 4. So of course we can take out okay, if we take out p common here, mm, 1 plus p square by 1 plus x square p power 4 plus 2x if we take common here, 1 plus this 1 plus p, sorry, 1 plus p by 1 plus x square p power 4. So now we can take this term common. So you get p plus 2x dp by dx times 1 plus p by 1 plus x square p power 4. Now leave this aside. All right. Look at this. This we can solve this. So p plus 2x dp by dx is equal to 0. Now taking this to the other side and bringing it down. Okay. So now integrating, we get log p is minus half log x plus say log c. So bring this to this side. So log p plus half log, so you get p times x to the power half. P root x is equal to c. So c is p root x. So which implies c square is equal to p square times x. So now we can write p square x as a constant. So in this equation, in this particular equation, you see, now the solution, therefore, substitute in the equation y is equal to 2px plus tan inverse p square x. So what we get here, so y is okay. P you can write as c upon root x, c upon root x. So you get 2c root x. And this is tan inverse of p square x is c square. So this automatically gives you the solution. This is a little roundabout way of doing it, but this is a method. When it is in this form, y is equal to 2px plus some function like this. So what we did, again, we differentiated with respect to x, wrote this in terms of p and tried to solve. And we got an equation, a differential equation in p. That differential equation we solved and we got a relationship between px and the constant, integrating constant. So now this we can substitute in the original equation to eliminate p completely. By that, we get the solution of the differential equation. So this is one type. Of course, solvable for x is also exactly like this. The equation is in terms of dx by dy. That's the only difference. Instead of dy by dx, it is in terms of dx by dy. And we can solve that this way. Next, this is an important equation. This is something that comes, Clairaut's equation. This is something that we can expect. Even if the first one and the third one we can expect, second one seldom we get questions on it, but that's a method for understanding. The Clairaut equation is like this. The equation of the form y is equal to px plus f of p, where p is dy by dx, is called as the Clairaut's equation. Now, how to solve this? Solution of this differential equation is like this. So y is equal to p of x plus f of p, some function of p. So dy by dx, which is equal to p, becomes, now when you differentiate this, it becomes p times derivative of x plus x times dp by dx plus f dash p into dp by dx. Okay. Now what happens is this p and this p get cancelled. And then dp by dx we can take out common. And we are left with x f dash p. This is df by dp, okay, is equal to 0. Now this is a derivative of the function with respect to p plus x. So this term will be in terms of p, this term will be in terms of x. This may not be 0. All right, can be, but may not be 0. But this implies that dp by dx is equal to 0. So we get p as some constant c. Therefore, the solution to Clairaut's equation, if you can identify it's a Clairaut's equation, the solution is very simple. Replace p by c. If it is of the form y is equal to px plus f of p, the solution is y is equal to cx plus f of c. Very useful solution. Let's go back to the previous problem. Okay, this is y equal to 2px. Little complication was there. It was not directly Clairaut's equation. But Clairaut's equation is y equal to px plus f of p. So example. Solve. Dy by dx is equal to tan of y minus x dy by dx. Now it is not directly a Clairaut's equation, but thoughtfully you take a tan inverse both sides. Now you get y is equal to x dy by dx. So this is equal to y minus x dy by dx. So if dy by dx is equal to p, then the equation is, take this px to the other side, y is equal to px plus tan inverse p. Now this is a Clairaut's equation. Correct? Because it's of the form y is equal to px plus f of p. Therefore, the solution is, don't have to do anything, replace p by c. This is the solution of this differential equation. Okay, one more. Solve. X p square is equal to yp minus a. Okay, where p is dy by dx. So take a to the other side, y times p is xp square plus a, divide by p, y is equal to xp plus a upon p. Now this is of the form Clairaut's equation, y equal to px plus f of p. The solution is, y is equal to cx plus a upon c. That's all. Replace p by c. That's the Clairaut's equation. So these are differential equations. This is the method of doing differential equations of first order, differential equations of the first order and higher degrees. Next, higher order differential equations. Let us look at linear. At the higher order differential equations. So we discuss within this category the linear differential equations. of second and higher orders. The first category. First, the definition. Just like in the previous case, y and its first derivative were of degree 1 and were not multiplied together. So similarly is the definition. The differential equations, the differential equation or the differential equation, okay, in which the dependent variables and its derivatives occur only in first degree and are not multiplied together. Is called a linear differential equation. Now, the most general form. The general form of a linear differential equation of nth order is like this. Nth derivative of y plus p1 n minus first derivative of y p2 n minus second derivative of y is the general form of linear differential equation where p1 comma p2 comma p3 and pn comma x are all functions of x alone. Okay, you cannot get a y factor here. If you get a y factor, then the y and its derivative are multiplied together. But the definition of linear differential equation is the dependent variable y and its derivative cannot get multiplied together. Okay, that is the definition. So necessarily P1, P2, Pn all have to be functions of x alone, and x also has to be function of x alone. In the first order linear differential equation, we didn't have the higher terms. We just had dy by dx plus py is equal to q, or this capital X, whatever it is. All right. So this was the form. Now here we have some function of x multiplied plus the second derivative multiplied by a function of x, like that. This is the general form of the linear differential equation. Now, okay. Now, this is the most general form, but we will. Okay, this is. Hmm. Now, linear differential equation with constant coefficients. This is one of the most important forms. One of the most important forms. This is nth derivative of y plus k1 times n minus first derivative of y plus k2 times n minus second derivative of y plus kn times y is equal to x, where k1, k2, k3 up to kn are all constants, and x is a function of small x alone. So if instead of these p's, we get k1, k2, k3 are all uh, constants, this p1, p2, p3 are all constants, then it is called as a differential equation with constant coefficient. All right. Now, this is called homogeneous. So in this particular equation, if that equation is 1, let us call this as 1, and then this equation is 2. Okay, then homogeneous linear differential equation with constant coefficients. If in 2 x is equal to 0, then the equation is called as homogeneous. Why it is called as homogeneous? Very simple, because every term is of degree 1 only. That's why it's a homogeneous. And non-homogeneous if x is not equal to 0. If x is not equal to 0, then equation 2 is called non-homogeneous. So how to solve the homogeneous equations, and then how to solve? So we'll just make a we'll just cover the theory part of it, and in the next class we'll start the problems. So homogeneous equations. So we'll discuss what is called as the superposition or linearity principle. Superposition or linearity principle applicable for homogeneous equations only. So if, so this is the theorem, if y1 and y2 are any two solutions of the homogeneous linear differential equation, then u is equal to c1y1 plus c2y2, where c1 and c2 are arbitrary constants, is also a solution to the differential equation. So for nth order differential equation, now this is if for nth order differential equation, if y1 and y2 are two solutions, that means y1 means y equal to some f1 of x and y2 is y is equal to some f2 of x. They are two solutions, then c1y1 plus c2y2 is also a solution. Now next, the complete solution of the nth order linear homogeneous differential equation is u is equal to c1y1 plus c2y2 plus cnyn. They are nth order differential equation, so you will have n arbitrary constants where c1, c2, so on up to cn are arbitrary constants. Now the concept of, so this is solution, this is now we talk about the general solution. Very important note for homogeneous differential equations. This is note for homogeneous. I'll just take 10 minutes more. I'll cover this and tomorrow we can actually do problems. So the first one is the general solution. U is equal to C1Y1 plus C2Y2 plus CNYN is called as a general solution to the homogeneous linear differential equation if, first condition, C1, C2, Cn are arbitrary constants, and B, y1, y2, and yn are linearly independent functions. That means, y1 cannot be x square and y5 cannot be x square. Then they are linearly dependent. Or y1 is x square, y5 is 3x square. They are linearly dependent. We cannot have functions like that. They should be independent. So then we have a definition of basis. The linearly independent functions linearly independent functions y1, y2, yn is called as the basis or the fundamental system. Basis is a better term of the differential equation. This is called as the basis. So the set of linearly independent, you will have n linearly independent functions at the max, and those n are called as the basis. Now, what is a particular solution? Particular solution is, in the general solution, the solution obtained by assigning specific values to the solution obtained by assigning specific values to the arbitrary constants in the general solution. This is called as a particular solution. Okay, this is called as the particular solution. Now, what happens? So this is what we are talking is about, for a homogeneous equation, what is a solution? What is general solution? What is basis? What is particular solution? Now, next we discuss the non-homogeneous equation. Non-homogeneous linear differential equation with constant coefficients. So let the differential equation the nth derivative of y plus k1 times the n minus first derivative of y plus k2 times n minus second derivative of y now. Now, interestingly, If the right hand side is 0, you get a differential equation. You get what you call a homogeneous equation. So now this can be split into two. So let U be the complete solution. Complete solution means the general solution for the homogeneous equation by setting x equal to 0. So suppose you put x equal to 0, you will get a homogeneous complete solution, the general solution for the homogeneous equation. Let V be the particular solution of the above linear differential equation. Okay, therefore, you see what happens. U is a complete solution. So we can write, replace y by u, we get this. That means for homogeneous equation, u is a function which we substitute in the homogeneous equation, it satisfies the equation. So this satisfies. And now what happens to v? V is a particular integral or the particular solution. It is a particular integral for this. So now we can add. Now adding, we get, because derivative we can by addition rule, u and v can be added. So u plus v plus n minus first derivative u plus v is equal to 0 plus x. So what we get is, this shows that y is equal to u plus v is a solution to the given non-homogeneous linear differential equation. So the solution to a non-homogeneous linear differential equation has two components. One is the homogeneous solution plus the particular integral. So U is called as, very important, the complementary function. U is called as the complementary function. Complementary function is solution of the homogeneous differential equation. So that we can mention here. Complementary function is the solution for homogeneous part. By setting x equal to 0. V is called as the particular integral. So everything rests in finding these two, complementary function and the particular integral. This is what we will see. So we use the concept of the operators now. This we know how the concept for homogeneous differential equation is, and for non-homogeneous differential equation is. How to solve that we have to see, but we fundamentally know how the solution looks like. Next, we introduce the differential operator. Okay, we denote d by dx as d, comma, the second derivative as d square, third derivative d cube by dx cube as capital D cube, so on. Okay, therefore the differential equation LDE, linear differential equation with constant coefficients can be written as d power n times y plus d power plus k1 into d power n minus 1 times y plus k2 into d power n minus 2 times y plus kn times y is equal to x. That is, if I take y common throughout, I will get a polynomial function in d times y is equal to x. All right, where f of d is d power n plus k1 d power n minus 1 plus k2 d power n minus 2 plus kn. So this is a polynomial function of the differential operator, and this can be factorized. This can be treated, which can be treated as an algebraic quantity and can be factorized. So this concept we will use in solving the differential equation. So now what we have done is we just found out what is linear differential equation general form, then what is linear differential equation with constant coefficients, what is homogeneous linear differential equation with constant coefficients, what is non-homogeneous linear differential equation with constant coefficients, What is the solution, general solution and particular solution for homogeneous? And for non-homogeneous equation, we can write the solution as two components. One is the solution to the homogeneous part, keeping the right hand side as 0. And when right hand side is not 0, the particular function that solves the differential equation, that is v. So u plus v will be together the uh, solution of the linear differential equation, non-homogeneous. So u is called as the complementary function and v is called as the particular integral. And the operator d d by dx, and d square is d2y by dx square, and so on. This can be used for the linear differential equation, and the linear differential equation can be simply written as f of d times y equal to x. And from here we will see how we can further solve the differential equations. All right. So we formed the basic background, but now in the next class, we will discuss how to solve the linear differential equations of higher order with constant coefficients particularly. All right, we'll stop now.